Hello, it's my great pleasure to introduce the second of the webinars of the online workshop, AI Development in the EOSC. This is organized by AI4EOSC project. My name is Marcin Płóciennik. I'm from PSNC and I'm the responsible in AI4EOSC for communication. Together with the organizing team that is also present today here with Judith Sens-Fabio, the project coordinator Alvaro Lopez and Valentin Kozlov, we prepared today the session about image processing with AI for EOSC. So first, before we go further, a few announcements. So just recently, we had announced the first release of AI4EOSC. So the AI4EOSC is a new toolbox for developing and running artificial intelligence models in the European Open Science Cloud. So we had also been communicating that, and there was also first webinar where we were going into general details about AI4EOSC, and the recording is also available. The other announcement, important announcement, is about the open call for new use cases. So basically, with the deadline of end of April, we are looking for new collaborations, new use cases. So if you would be interested after all this webinar, just get in touch with us and please submit your application. So there is also, if you are going to attend EOSC Symposium, we propose there also the session about unleashing synergies for fair AI development in the EOSC. And if you find it interesting or you'd like to join, please vote for us. And here is the QR code for that. So today we had 4 very interesting presentations. Basically, the impact of AI in scientific image processing, image segmentation, enhancing satellite imagery with AI, and at the end train an AI4EOSC module. So without further delay, I would like just to also say that you can post your questions and comments in anonymous way. So just join us at slido.com and put 2960746. So also QR code here is available for scanning. So okay, without further delay, I would like to invite now Deborah. Sorry, I would like to invite now Deborah Schmidt. A second. Okay, sorry. Deborah Schmidt, that is the head of the HELMHOLTZ Imaging unit at Max Delbrück in Berlin. She is a media computer scientist. So she specializes in scientific image data analysis, and also she's interested in citizen science, and she's quite an enthusiast on the open science. So she's from HELMHOLTZ Imaging, Max Delbrück Center. So Deborah, the floor is yours.
Thank you so much. Let me share my screen. Hope you can all see that.
Yes, we can see. So you can start.
Wonderful. So thank you so much for inviting me to this AI4EOSC webinar, and so that I can talk about the impact of AI on scientific image processing. We've already heard about what AI is and what kind of deep learning architectures exist in the last webinar of the series, so I will focus more on concrete applications and publications regarding this topic. Since I'm not from AI4EOSC, I want to give you just one slide background information about my association. I belong to HELMHOLTZ IMAGING. HELMHOLTZ is Germany's largest research organization, and HELMHOLTZ IMAGING is a platform initiated by the HELMHOLTZ Information and Data Science Incubator. Our mission is to unlock the potential of imaging in the HELMHOLTZ Association across research domains and along the entire imaging pipeline. That means that we offer support and we develop solutions for scientists within and beyond HELMHOLTZ for various topics along the imaging pipeline. I'm leading one of the support and engineering units of HELMHOLTZ Imaging. I'm located at the Delbrück Center for Molecular Medicine in Berlin. This talk will not be about HELMHOLTZ Imaging. I will focus on the impact of AI on image processing based on the experience we've made in our daily work. And I'm looking forward to explore more synergies with AI for EOSC as well. In the first part of my talk, I will go through examples of advances and AI-based tools in scientific image processing. Of course, I can only scratch the surface here. Let's kick this off with one example of astrophysics at the very beginning of the pipeline where images are first constructed. Here's the famous reconstruction of a black hole on the left. What you can see on the right here is an improved version of that black hole simulation acquired with a method called Primo. The ring here is thinner and also has finer details. This was achieved by using machine learning to learn the correlations between the low frequency and the high frequency structures from these simulations. And this enables us to get like a better data visualization, even if there's sparse coverage of data. Let's talk about another method for enhancing the image quality using content-aware image restoration, pushing the limits of fluorescence microscopy. And what is done here is what you do usually with a classical unit, you train it on in this case, a low quality and a high quality data set. That means you can, for one experiment at the beginning, acquire high quality data and then train the model on like this transition from low to high quality data. And then, for example, using a longer exposure. And then for the rest of the data, you can apply this model and continue to acquire the data on low quality settings. This is super important, for example, for faster acquisition and less destructive acquisition. It can be used to restore low photon exposure settings and also for isotropic reconstruction of undersampled images. This is what you see here in this example. If you apply a trained model, you can acquire resolution in the z-axis extremely nicely. Now, what if we don't have these kind of training pairs of low and high quality? We can still do something using AI. The example here is called noise to void, a method where all you need is a noisy image data set and then where the noise is independent of the pixel location. Since we do not have these noisy and denoise training data sets, the method uses the noisy image both as the input and the output and the target of the model. And then the model, that's the trick here, has a blind spot where from the input image, it will not be able to see the pixel it's trying to predict here. And that means it has to learn the value of this pixel based on the context of the neighboring pixels. This works super well for a smart denoising method that was also implemented as a feature plugin back then. So it was made accessible for users in the bioimaging community here. And now it's also available as an Apari plugin, making it much easier to apply this to existing data. Moving along the imaging pipeline, segmentation is, of course, a highly requested task in image processing. For deep learning-based segmentations, UNets are usually trained on annotated training datasets, but the configuration of the training is not necessarily trivial for scientists without a computer science degree. The tool I want to highlight here is called NNUNet. It only needs the annotated training set and then will derive a fingerprint of the problem, meaning that all the parameters based on the data are picked based on the data from configuring the most suitable UNet. And this approach has won several competitions just out of the box by applying the method to the competition training dataset, and was developed by my HELMHOLTZ Imaging colleagues at the German Cancer Research Center in Heidelberg. Now, the previous example was optimized to perform well on any kind of data from any kind of segmentation data from any domain. Other tools focus more on specific domains like this one here. So cellular segmentation is a highly common task in bioimaging. And CellPose has just brought the community a huge step forward by providing a user-friendly interface and pre-trained model for a variety of existing cell types. It includes a routine for human-in-the-loop training to fine-tune existing models using your own data. And it was just extended. There was just a new version out that also includes denoising, deblurring, and upsampling. So just extremely impressive. AI can also be used for more explorative strategies. This example, called Terror Pattern, is a prototype that was initiated by a new media artist for immersive exploration of satellite images a couple of years ago already. This project used the deep learning model called DCNN, was a ResNet architecture trained on hundreds of thousands of labeled satellite images from OpenStreetMap to recognize different place types. This training taught the model to identify the key visual features for satellite image classification. The model was then adapted for broader use by focusing on a layer just before the classification, and this enabled transfer learning, where one can now search for and identify similar looking areas across major cities using a fast search algorithm. You can go to that website and just look it up. You can go through the satellite data and click on an area. For example, we see here, you could pick a golf course, and it will locate other similar looking area in the map. And the same is done here for school buses. Moving on, one difference between everyday image processing that we might do with our phones, for example, and the scientific image processing, we have the access to a variety of imaging modalities, which of course comes with challenges, but it's also a huge source of potential for AI applications. Here are just two examples. First study looks into combining different types of data, such as color images, near-infrared, thermal and terahertz images in different stages of training the deep learning model. So early on, in the middle, and late in the process. And that helps to recognize types of bulky waste. The second method used artificial neural networks to estimate soil moisture from satellite imagery. And they also employed here a comprehensive approach by extracting the features from multiple satellite sources at once. This was validated together with an extensive field campaign and spatial distribution analysis across various scenarios. AI can also be used for synthetic data generation and can be embedded into whole workflows spanning across the entire imaging pipeline. What I'm showing here is a research project from my group together with researchers from HELMHOLTZ Munich and the University of Stuttgart. What our colleagues do is they sample lung tissue, and we then analyze it, we segment it, we generate meshes from this, which are printable by our colleagues in Stuttgart with their bioprinting machines, which is pretty cool. Now, what we can do here is, with the data that we acquire, we can train a generative model to generate even more lung tissue data. And the goal here is that you can image lung tissue from someone with a defect area, and then you can replace this with generated healthy lung tissue and bioprint this. That would be pretty amazing. In the second part of my talk, I want to now briefly discuss the challenges of AI applications in scientific image processing, because as exciting as all these examples look, there are definitely many challenges, and I also want to mention some available resources addressing these challenges. First, let's talk about how to apply AI-based methods. In the first part, I showed examples that I picked specifically because they had user-friendly interfaces. This is sadly not often the case, especially if we look at software publications in computer vision. They're often hard to reproduce and lack user-friendliness. Novel AI processing methods are also often optimized for natural images, which are usually like more 2D or 2D like videos, and not necessarily be able to coping with the diversity of scientific image data sets. Then there's this blurred line between the user and the developer. So yes, we can integrate deep learning systems into our applications for scientists, but once they need to figure out what's actually happening, once they want to fine-tune something or adjust parameters, they are confronted with a lot of words that they can't really, that they don't know, or that are really hard for them to address. I think there's this education that is missing here is like a big challenge as well. That means that not just that, but also for experts, validation of results can be challenging. It is also related to bias in the training data, which is sometimes even if you know it as well, but also sometimes really hard to detect. And of course, the challenge is also the resource availability. Not everyone is able to train models with their available resources, and it's also super important to be conscious of the usage of resources. Sometimes people just want to apply AI to something, even though there might be simpler methods available to do the same thing. Now let's go to some resources addressing these challenges. The first one is a wonderful publication called Community Developed Checklist for Publishing Images and Image Analysis. I would highly recommend checking this out. It includes these checklists that also include steps for following fair publications of machine learning workflows, and this can be really helpful. Open science is a big topic in making sure that we know what we're actually doing here. And the second one I just want to briefly mention is a tool my group is developing and maintaining. It's called Album, a framework for scientific data processing with software solutions of heterogeneous tools, which provides a user-friendly way of wrapping specific software use cases into short Python scripts, including the metadata such as citations and also something like the virtual environment description. You can bundle these into topic catalogs and then host them decentralized on GitHub or GitLab. And then Album provides you with the user-friendly interface for running each of these software use cases in their own virtual environments. I won't go into detail here, but if you're interested, feel encouraged to reach out to us, please. Now, I've mentioned validation a couple of times. In order to validate AI-based results in scientific image processing, we need well-curated, open, and annotated data sets. These are pretty hard to find. Here are 3 resources for getting better annotations. The first tools are just tools that our users use on a daily basis. One of them is Elastic. It's just an incredible tool for machine-based labeling, and it also includes, can guide users through the AI-enhanced labeling workflows. LabKit is specifically built to support large-scale image data sets. You have the link here on the right. I'm listing here one publication by Tim Rich. He's a HELMHOLTZ imaging scientist who wrote with his colleagues about how important labeling instructions are for the quality of biomedical image analysis. So describing how the manual labeling process was actually done. and how these are sadly often lacking from scientific publications of annotated data sets, also really worth checking out. Once one is in possession of a validation data set, the question of how to correctly compare the results to this data set is a whole another topic for research in image processing. And that's not just true for AI-based methods, but also particularly relevant here because we want to automate processes further, and correct validation is the key to doing this responsibly and successfully. This publication I'm showing here called Metrics Reloaded Recommendations for Image Analysis Validation is a super long document with like expert knowledge on where to choose which metrics, and they have developed this easy to use website where you can go through the content of this long document basically by just answering a couple of questions about your problem, and it will automatically guide you to the best way of validating your processing step, and also pretty like high recommendation here. One last challenge I want to mention, and I'm not really sure how we will deal with this in the future, is the question about how much we can actually trust published image data. There are good chances that you know Elizabeth Big. She has gamified image forensics on Twitter by posting these challenges regularly, where others can hunt duplications in publications, including images. There's one example here on the left. Many of them are often plain copy and paste situations, which obviously exists and people's, like, it happens, but how will we be able to even deal with this in the future with deep learning based fakes in scientific imaging? Big question for me. Talking about the future, and not just negatively maybe, but like what's going to be big in AI-based imaging processing in the future. Now, of course, large language models are a hot topic right now. They now pass their way into individualized workflows that you can build, that users can build who also do not have like scientific computing experience necessarily. I want to cite Luc Royer here from The Future of Bioimage Analysis, a dialogue between mind and machine. And he says, "We're currently living in a transformative period in which the century-old promises of AI are rapidly becoming reality." This is exciting, but I'm also super curious how in this process we will make sure that we know what's actually happening under the hood. Now, one method that we can use here is explainable AI. This is not necessarily a new topic. It's been here for a couple of years. What I'm showing here, images from a publication called "Why Should I Trust You? Explaining the Predictions of Any Classifier." And you see that you have this image, and then through explainable AIs, you can highlight which classification results is based on which parts of the image. So for example, if this is a Labrador, then the model learned this from this part of the image. And this is also especially great if you're trying to understand why something went wrong. So for example, in this case here, there's a husky classified as a wolf. And you see that the pixels that were relevant for it kind of looks like white fur. So it makes a bit more sense, but it's obviously not what you're trying to classify here. Now, even though these methods exist, I haven't seen them too much applied in user interfaces, and there's a lot of research going on in the topic as well. So I'm looking forward to seeing this more integrated in user-friendly ways so that we can actually access this kind of knowledge. Multimodal image processing was already mentioned before, but it will play a more important role in the future as well. Citing here from Imaging, the Future of Optical Microscopy, Everything Everywhere All at Once, they say, a complete picture of how life functions can only be attained if we leverage all these technologies together. In essence, we reimagine the future of optical microscopy, wherein we can imagine anything, anywhere, at any time. With AI-based methods, especially large language models, foundation models, this can actually now become reality. And there's a lot that's coming towards us in this direction. So we can now feed all of these different sources, all of these different modalities into one model. Foundations models are extremely compute intensive, so you wouldn't do that for solving singular tasks, but you can imagine that you have, for example, everything we know about the human, we all throw that knowledge together into one model, and then the model has its own representation of what the human is. And then we can use this to fine-tune this with much less compute time for specific tasks. And this can be really relevant for so many topics that we haven't explored in that detail so far. So especially for the digital twin scenario and individualized healthcare, from this example in the biomedical domain, there's a lot to come. Now, while this all sounds great, I think it's still super important when we work on these big scale applications that we also track the impact of AI on a bigger scale. The UN Sustainable Development Goals, of course, play an important role here. In this publication about the role of artificial intelligence in achieving the Sustainable Development Goals claims that there is a lot of research to be done in this area. I want to cite them here with the problem is that neither individuals nor governments seem to be able to follow the pace of these technological developments. So the question is, are we making informed decisions when we use novel AI-based methods in scientific image processing? And I find these conversations highly valuable to make sure that we are not just keeping a good eye both on the advances AI is helping us to do in scientific image processing, but also on the price we are paying for it. With that, I'm at the end of my talk. This is the HELMHOLTZ Imaging team. I want to thank them all, and I want to thank you for your attention. There's the HELMHOLTZ Imaging website link here and our support email address, with anyone also outside of HELMHOLTZ Imaging can use, for example, for maybe exploring synergies, and my personal work email address here as well. Thank you so much.
Thank you, Deborah, for this very good presentation, very interesting. So looking in the questions, we have basically some questions from the audience. So the first question is, do you think the generative AI can be used to generate new images as a data augmentation technique?
Yes, I'm fully convinced that is possible.
Okay.
I think it's also already happening, yes.
Okay. Next question, can you summarize what are the fundamental steps to follow in general for an accurate image processing based on AI techniques?
Sorry, can you repeat that?
Yes. Can you summarize what are the fundamental steps to follow in general for an accurate image processing based on AI techniques?
Okay, so the question is what steps to take to make sure that the AI-based image processing results are accurate.
Yes.
Is that correct?
Yes.
Yes. So there was just a very interesting discussion on image.sc, the forum, which I can also highly recommend, on a tool that was just published for a novel segmentation method, and they kind of went through this process of figuring out how well does this actually work. And basically you need open science on all of the different aspects to know if this is a method that you can use and it produces the results that you want. So the data that the model was trained on is of course extremely important. The access to this data is important. But then the labeling instructions, checking these, knowing if they actually match the model. So in the discussion that I was just mentioning, they figured out that in the labeling there was cell segmentations, and there were some blurry cells that were not labeled in the training data set. So the best model was also not tracking these in the finally trained model. And this is something that one needs to be aware of if that's matching the kind of use case that you have. So this is important. Then it's really great if one has comparative strategies, so non-AI based methods to compare to, also super helpful. This is what comes from the top of my head.
Okay, thank you so much. Just looking if there are next questions. Yes, you have mentioned several models and methods. Which are the most used models nowadays? Is it UNet, YOLO?
I'm sorry, I don't know that. So one thing we're also looking for is where are models hosted? Maybe an interesting topic here, because there are multiple model zoos. I didn't include that now, but if you have a model zoo where models are uploaded, then you can also track which ones, potentially track at least to some degree, which models are uploaded and downloaded. So I would also be curious about the strategy for like AI4EOSC. Do you have a model hosting strategy or like that would enable us to track something like that?
Okay.
So from my experience, it's still a lot of like basic UNet usage, because it's just performs very well for many use cases. But there's so much more now coming up, of course.
Okay. Thank you again for this presentation. I think there will be an opportunity to further discuss with you and AI4EOSC. And for the audience, I would like just to remind, just in case, I will show maybe again the link to Slido. Just if you give me a second, just okay, here is the link to Slido. I hope you can see it. You can scan it if you have not done it before. That's for a second, okay? And what is also important to say, we are, as AI4EOSC, looking forward to your feedback. So basically, besides asking a question, you have their polls. And there are like a few questions we'd like to ask you, like what would you like to learn more about in upcoming events, and few other questions. So there was a final question to Deborah, to you, I think. What are the most interesting research gaps in AI image processing in the healthcare domain? I saw that there is an
so which kind of gaps there still are, you mean?
What are the most interesting research gaps in AI image processing in the healthcare domain?
So again, this is a difficult question. Definitely interesting to discuss and not just answer with like from my side. I've read a couple of years ago in a piece about the future of AI in biomedical image analysis that whole workflows embedded into AI models might play a more important role. haven't seen that too much. It's still like pieces that you bring together, and I wonder if that might be something where more might come up, so that we have just more complex tasks. But I'm also happy with making sure we understand what we understand by tackling tasks bit by bit. So yeah, but definitely leading to a. So I'm very interested in this patient-centric custom diagnostics field. Also, as a diabetic who has like seen how open source development and open science has revolutionized how patient care can happen if patients are to some degree in control of what's happening and what they can do with their data. This I'm very interested and passionate about, to see like if we make AI applicable and usable and user-friendly, how far can people go outside of the big scientific clusters with these methods?
Okay, thank you again for all the responses. And we now move to our next presentation.
Thank you so much.
I'd like to invite Saúl Cano Ortiz, that is PhD candidate in the artificial intelligence applied to civil engineering, data scientist and physicist. Currently, he's working at GTECO, University of Cantabria, as R&D data scientist, and his main topics are computer vision, deep learning, and generative AI. So, Saúl, the floor is yours. You can share now the screen.
Okay.
I can see the screen, so you can start, please.
Okay, so today I will be talking about image segmentation with AI techniques, but basically I'll be focusing on a question that was made just right now about making data augmentation for segmentation architectures with synthetic frames in order to improve regular standard segmentation metrics. Okay. So basically, I will cover very briefly different segmentation challenges. I will also mention very briefly state-of-the-art segmentation architectures. I will talk about possible solution, which is data augmentation with synthetic samples. And then I'll discuss a little bit more deeply into state-of-the-art generative models. And I think that I will arrive to the current generative architectures. And finally, I'll show a personal real-world application, which is intelligent road maintenance, and the main conclusion. Okay, so basically, talking about 2D computer vision tasks, we have mostly classification, object detection, semantic segmentation, instant segmentation, post-measuring, etc. And today we'll be focusing on semantic segmentation, which is pixel level classification. As you can see here, I'll be all the time using this example of pavement stress detection, which is the real world application I was mentioning. So as you can see, the output is a background image with pixel colors depending on classes. In this case, longitudinal crack, manhole, and also a seaware. So image generation means to produce fake images, which means an image as the left image, but from semantic masks. So basically, it's the inverse problem of semantic segmentation. Is it's called semantic image synthesis. And basically, the benefits of using segmentation architectures is that they give you rich image understanding because you have pixel level information. Also, the applicability is, as Deborah mentioned, and also you can compute geometric aspects such as areas, lengths, or I don't know, widths with skeleton types algorithms. And the drawbacks is the computational cost because of the high level precision. And the main problem that we will be discussing today is that segmentation architectures, as every deep learning architectures, they are data driven. So they need a large amount of label samples. And as you can imagine, it's not that easy to get, not even just the data set, but also to label it. And of course, it's quite harder for segmentation problems than object detection problems. And then there are also other issues such as pixel and class imbalance. Okay, so segmentation architectures, as it was mentioned, I think that the most used one is UNet, but it was published in 2016. And basically, many variants of UNet have been published, such as SegNet, PSPNet, LinkNet, etc. And right now there is quite a hit. I mean, I would say a hot topic with transformers because they were created for text, but right now they are being used with visual transformers with images. But basically, the idea is that right now there are also really complex architectures, but mainly based on UNet, where the idea is to compress images in order to get more, let's say, patterns or low patterns, and then the decoder just establishes the resolution, and the output is the segmentation mask. So right now I'll be digging into the inverse problem, which is data augmentation with generative architecture. So basically imagine that you don't have a lot of images, that you don't have a lot of label data. The idea of generative architecture is to receive as an input the real mask and the real image. So you can imagine, okay, then what's the benefit? Because we also need to label. The thing is that you have to label really few images, and then once the generative model is trained, if it works, you can generate thousands or just as many images as you want, so that you can just train a segmentation architecture with real and fake images, and always to validate with just real images. So right now I'll be talking about generative models for segmentation, semantic segmentation in synthesis. The most typical one is generative adversarial networks, and there are many variants. So the idea is that there are two networks competing in a fight. So the generator just receives the mask and outputs a fake image, and the discriminator receives real images and fake images and outputs if the income images were real or fake. So basically the generator wants to trick the discriminator, and the discriminator do not want to be tricked. There are benefits of using these conditional generative adversarial networks. Conditional because you give the mask as input. The training inference, it means you can create thousands of images with a powerful GPU in seconds or milliseconds, depending on the images and the specific GAN, generative adversarial network you are using. They can be really realistic looking. And the drawbacks are generalizability, which means that they can cover maybe, in this case, a type of road distress, but they cannot cover others, and also mode collapse, because they start to create always very similar images, which is not really good to generate a diverse data set to train a segmentation architecture after augmenting the data set. And basically, the most used architectures are pix-to-pix and also CycleGAN. So yeah, pix-to-pix is the one I was mentioning. It's a type of GAN. And then CycleGAN is quite more complex, but basically it employs the cycle consistency method. And instead of training 2 networks, you have 4 networks. So you have 2 generators and 2 discriminators, which is more complex. I mean, generally, when you train this, you just need to put a batch size of 1 because it's really quite complex. So it's the same as pix-to-pix, the previous one, but also with the problem of complexity. And today, I wanted to talk about diffusion models, which I'm more familiar with. Is like, I think the hot trend right now. And diffusion models are becoming famous because of the results. And the problem of diffusion models is the time that takes to create images. But diffusion model, talking briefly, you start from noise, and what you do from noise is to create image. Basically, you denoise the images. So you have 2 processes, the forward diffusion process. So you can see you start from a real pothole in this case, and then you get pure isotropic Gaussian noise. And then the idea is to use a network to predict the mean noise for each time step, because I didn't mention it, but this is like a Markov chain. This is a time step process. You add Gaussian noise and you learn what is the mean noise at each time step, but reversely. And then there are formulas in order to get these new images just from noise. And I just wanted to talk about one that is very recent from 2023 that can create from segmentation masks these images. So as you can see, you are going to give the mask, and the output is going to be a very realistic looking image. And I don't want to really enter into the architecture, but basically you include the segmentation map with a type of attention mechanism, which was confected for semantic segmentation. And right now, like the most used generative model also for semantic synthesis is latent diffusion model, but the idea is the same, but the difference is complexity. So instead of giving us input noise, what you give is the output of an encoder, like a regular variation autoencoder. So you encode this noise, so the dimension is quite smaller. And then you basically perform what I was mentioning, this diffusion model. And then the output, what you do is decompress it with the decoder of the variation autoencoder. And then you can give as condition also the semantic map, but this paper was published with other type of conditions such as text or even images, I don't know, just to perform maybe image colorization, or, I mean, there are many type of conditionalities. And I wanted to show our approach. So what you are seeing here is a trained generative model that can create fake images from semantic maps. So these maps were done with paint, and the results, it's basically the same. So here you have to see the conditionality that the mask is also present in the RGB image, and also that the mask is realistic looking. And then what you do is you include these synthetic patches with the masks in the real data set, and you can create thousands of images. And as you can see here on the left part, this is the workflow that we developed in order to improve segmentation architectures. And then we improved different type of models, not just, I mean, we used segmentation models also for object detection model augmentation. And basically we created a full system to automatically detect defects, but powered with generative AI. And then the main conclusion is that segmentation are data-driven. So it's interesting because mainly the papers focus on narrow architecture sets, which means to develop more complex models, which is good. But the thing is that you have to remember that it's also about data quality and the effort of label data once you have it, which is also difficult to collect quality and diverse images. And then, for example, if you have problem of class imbalance, you can collect more images. But if you, for example, in this case, go to the road, it doesn't mean that you are going to encounter, for example, these underrepresented defects. So it's a really good tool to create thousands of images, and thousands of images that are conditioned. You can do it with, for example, hand-painted pictures. And then you augment the data set, always this train partition. And then you validate it always with real images in order to improve segmentation architectures. And thank you so much. This is under the project MAPSIA. And that's it. So thank you so much.
Thank you so much for your presentation. It's a very interesting subject. So we are getting some questions from the audience. Let me have a look there. So how are the images captured for road condition monitoring processed? What special tools are used?
Okay. Basically, what we did is to we used a camera, and we put it with a 3D printed system in the rear window of a regular car, and we just drove and collect these videos, and then with OpenCV, common computer vision library, which is split the videos into images. And yeah, and to process the data, then we start labeling the data for an object detection problem. We saw that there was low detection for less represented classes. Then we use YOLO V8 object detection architecture. And to improve this, the model is published. You can look for it. We publish a denoising diffusion probabilistic model to create just from labels synthetic images in order to improve YOLO V8. And right now we have developed same thing, but for segmentation architectures with segmentation maps.
Okay, thank you. I'm looking, there is next question. What is computational cost of training these models for the case of pavement monitoring, and how many images do you need to collect?
Good question. Good question. I mean, the cost. The cost with a diffusion model is not that high. It depends on the unit architecture that you are using. The thing that is really not cost, but it takes time. It's sampling images. The difference, for example, in comparison with generative adversarial networks, is about a factor of 10 or even 100. So train a diffusion model. I mean, you need a GPU, but not a really powerful GPU. And a training, for example, for 1,000 images of 128 by 128 would take more or less 5 to 10 hours in my GPU, which is 3080 NVIDIA GPU, but it depends on the GPU.
Okay, thank you. There is another question coming. How do these results compare to results from segment anything model SAM?
Honestly, I've just tried this SAM model from Meta, and with my images, and it was not really good. So, but obviously, I just validated with a couple of images with this open source tool they have online. And I didn't compare it like with image quality assessment metrics or like more technical. But basically, I think SAM is really good for objects where the borders or the corners are really well defined. But for example, in a problem for such as pavement detection, where the difference with the background is not really, as when you detect a regular object, it didn't work basically. And I think SAM is good to improve segmentation of regular objects, but if the difference with the background is not really high, it doesn't work.
Okay, thank you. And the final questions I see, basically this is about the relation with EOS. So where does EOS can come into play? Is EOS providing a compute platform where you can train your models? Is EOS providing a trained models that can be used?
For example, the way I see it, could be interested to use basically I don't know, more power in order to just develop some parallel computing strategy in order to just reduce this training time and also obviously the sampling time. So I think that would be the better to embed the model in order to just accelerate the training and inference process.
Yes, and I think the additional response to it is the AI4EOSC platform that could support you as well in all this process. So, okay, with that, I would like to thank you again for this very interesting talk and all the answers that you gave. And now I would like just to remind again that also in YouTube, you have a link to the Slido, you have a link to both to ask, so you can ask questions, but also you can provide us with the feedback for the next webinar. Your feedback will help us also improve what we provide to you. So basically, without further delay, I would like to invite Daniel García, that has PhD in Science and Technology from the University of Cantabria in the field of artificial intelligence applied to remote sensing. He's currently working as a postdoctoral researcher at the Marine Sciences Institute of Andalusia. So please, Daniel, the floor is yours. Please share the screen and you can start.
Thank you so much, Marcin.
Can you put in full? Okay, thank you.
Yeah, it's okay?
Yes, it's okay. Please go.
Okay, so well, it's a pleasure for me to participate in this webinar. Good afternoon, everyone. As Marcin said, my name is Daniel García, and I'm going to talk about the multispectral satellites and how to increase or improve the spatial resolution of their images. I would like to start the presentation with a brief introduction about the multispectral satellites, one of the most well-known type of satellites, because this kind of satellites capture images of different wavelengths of different electromagnetic spectrum, providing valuable information about the spectral signature of the Earth. Generally, there are two types of sensor on board of these satellites: the multispectral sensor, which capture multiple bands at different wavelengths, but at low spatial resolution, and the panchromatic sensor, which capture a single spectral band, but at high resolution, at high spatial resolution. And this happens, and this occurs due to the inherent physical limitation in the design of the optical or multispectral sensor, creating a trade-off between the spatial and the spectral resolution, so that a single sensor cannot capture images with a high spectral and spatial resolution simultaneously. It is worth mentioning that spatial resolution refers to the size of the smallest object distinguishable in an image, that is the size of the pixel, and the spectral resolution indicates the number of the width, the number and the width of the spectral bands that the sensor can discriminate. Therefore, a single sensor cannot capture several spectral bands at a low spatial resolution. Sentinel-2, for example, is one of the most well-known multispectral satellites. It captures 13 spectral bands with a spatial resolution of ranging from 10 to 60 meters, depending on the part of the electromagnetic spectrum, and has a revisitive time just 5 days. Landsat 8 is another well-known multispectral satellite. In this case, Landsat 8, it captures 11 spectral bands. 10 of them have a spatial resolution of 30 meters, and one panchromatic band has a resolution of 15 meters. The revisitive time of the Landsat 8 satellite is approximately 15 days. But they are not the only multispectral satellite that exists. In addition to Sentinel-2 and Landsat 8, there are other multispectral satellites such as MODIS, BIRS, WorldView, or Aster, for example, and each of them with their own spectral bands and spatial resolution. So the concept behind enhancing or improve the spatial resolution of multispectral images is to improve the low resolution bands to match the high resolution of the panchromatic band. This can be achieved by merging the information from the spectral band with the panchromatic band. And this technique, sometimes known as pan-sharpening, was implemented using various algorithms, which can be categorized in 4 different main groups. The first one, the component substitution algorithms, where the component of the original multispectral images are transformed to isolate the spatial information, which is then combined with the panchromatic image to create a fused image with high spectral and spatial resolution. The second, for example, could be arithmetic operation, which involve algebraic operations between the multispectral and panchromatic bands to generate fused image. Another one is high-frequency injection algorithms, which extract high-frequency components from the panchromatic image and integrate them into the multispectral image. And finally, the last one is the multi-resolution analysis, in which decompose the multispectral and panchromatic band into different scales or resolution to extract the spatial details, which are then incorporated into the multispectral bands. However, the new methods developed for these techniques involve the last deep learning techniques, the convolutional neural network, for example. And the idea here is that by providing the network with all the spectral and panchromatic bands of the satellite, so that the network can learn to improve the spatial resolution of the bands. The training of this network is therefore carried out by degrading the original spatial resolution of the bands and teaching the network to transition from the degraded bands to the original band. This way, once trained, the network is capable of predicting the necessary step to enhance the spatial resolution. For example, with Sentinel-2, which increase images at 10, 20, and 60 meters. In this case, we have two different neural networks, one to improve the resolution of the 20-meter bands and another to improve the resolution of the 60-meter bands. And in this case, for example, for the 20-meter bands, to train the network, we degrade the band to the same spatial scale that we have to improve. That is, as we want to enhance the resolution from 20 to 10 meters, we reduce the resolution in the same proportion to 40 meters. This way, we train the network to transition from 40 to 20 meters, and then we can make the prediction to transition from 20 to 10. The case of the 60-meter bands will be similar. We input the network to take the step from 360 meters to 60 meters, and once trained, we will be able to predict and take the step from 60 to 10 meters. This training approach assumes that the image texture behave similarly at different scales, and this allows the application of image processing methods that rely on spectral correlation to enhance resolution or performs other operation effectively. And now I would like to present a brief tutorial on how you can work with this tool from the AI4EOSC platform. For this, I have placed some links here, such as the marketplace link. And if we click, for example, in the link of the marketplace, we can open the platform place. This one. Well. Okay, this is the marketplace page where you can find different modules from various applications. And one of these modules is the upscale multispectral satellite, which is this one. If we click on the model, yes, if we click on the model, we can find information about the tool, such as the satellite we can currently work with. And for example, in the training section, there is the GitHub repository with the code and more information about the tool. If we are logged, sorry, I think I have closed the dashboard, so let me open again. Sorry. Okay. Upscale multispectral. Okay. So if we are logged in the page, we can find two different buttons here. Give me a minute to log and continue. okay, these two modules. And if we click on the train module button, a small questionnaire opens up to configure the machine on which we are going to launch the application and work with, and the machine with work with. As the title is a mandatory to write a title or name of the deployment, we put one and move to the next step. For example, go to the next step. And here we configure the characteristics of the machine we want to launch, the number of the CPUs or even the GPUs if it's necessary. I thought it's not required in this case. The amount of, also we have to configure the amount of the RAM and the amount of the disk, the amount of the storage. And for example, in this case, I recommend setting a relative high amount of RAM, for example, 16, and well, 8 CPUs, I think is okay. So click next. And well, here we can configure cloud storage if we have it or need it. But if not, the default settings are fine. So we click on submit and wait for the platform to launch our machine. Of course, this deployment occurs physically, and the larger our processing requirements, the longer it may take for the machine to be ready. So click on submit, and well, when we click submit, the page takes us here, and here we where it shows the status of our machine. In this case, it is still pending or starting, but I already have one that I launched this morning, just in case it takes too long. So let's wait a minute, and if not, we will proceed with the one I already have running. Okay, it's okay. So here, clicking in this button in Quick Access, we enter into the super resolution tool, and here we can find different options. For example, to retrain the model, or if we already have one training, also information about the status of training of the training. Finally, the last button, this one, is to make predictions. And to enhance the resolution. If we click on predict and also in try it out, here we can configure several fields depending on what we want to work with. The first section or the first option is for attaching the original file that we are going to work with. In this case, I'm going to upload a zip from Sentinel-2, sorry. This one, the original zip file. Okay, I think, yep. And this field, for example, is to select the satellite, which is in this case also Sentinel-2. The next two options, this one, ROI XE test and ROI lat-long test. These options are if we don't want to work with the entire image and we want to crop a piece, either by a pixel position or by coordinates. I am going to select a small portion of the image to speed up the process. So, for example, that is okay, I think. The next section is if you only want to work with certain bands and not all bands, or not all of them. And in this case, I will leave it as it is include all bands. And finally, the last two different options, you can configure the output format, specifically the path or folder where you want to save it. In my case, I leave it as it, and when configured, you click on execute. On the machine start to working. So click on execute. This may also take a few minutes, so while we wait for it to finish, to conclude the tutorial, I would like to show the bands at high spatial resolution and the different compared to the previous one. I also have a test I did this morning, so I can show it until the new one finish. Well, since the format is GeoTIFF, we can open it, for example, with QGIS. If I open the file with the bands at high spatial resolution and the original bands, we can see the difference. Let me this is the original band. So I'm going to open, for example, the 8th band, for example. And now I'm going to open the super resolve bands, the FUSH band. This is the super resolve. So sorry. Yeah, this one. So this is the original band and the super resolve band, and when we zoom in, the original band appears blurry and pixelated. However, the image with the spatial resolution appears sharp. It's really too black. I don't know why. Okay. I don't know if this one is finished. So really to download the file is only clicking download file, and well, you save it and it's okay. And now we can open also the new image. This one is the new image. So I'm going to set the same band. Okay. Yes, the original band is blurry and pixelated, and the new band is much better. This one is also with the other bands, for example, an 11 or another, for example, 6. Okay, and well, that is all from the tutorial. So questions?
Yeah. First of all, thank you for this very interesting presentations and demonstration. So it's really looking good. So here, let me look into questions. So there is, maybe because I see one question that will be more to me, so we will go to it later on. But I see the question maybe more to you. The cost of the training these models for super resolution is very high from a number point of view. Are there any special requirements to take it into account?
Well, from this point of view, from a storage, really no, but from a RAM point of view, yes. We have to keep in mind that, for example, the Sentinel-2 images are like 100 pixel by 100 pixel, and if you need to work with the entire image, you will need a lot of RAM. Yeah.
Okay. Thank you. So another question, what are other applications of super resolution beyond satellite imagery? In what other use cases have you successfully applied and tested it?
Well, you can also apply super resolution to the normal image to improve the sharpness of the image. But this kind of application are aimed at satellite image. But for example, for other application, well, for example, now we are working from the same approach on fusion data from different satellites. For example, we are trying to merge the band of Sentinel-2 and the Sentinel-3 satellites to create an image with very high spectral resolution and very high spatial resolution also.
Okay, thank you. So I don't see here. Okay, there is a question, and this I will take over. As the EOS portal marketplace will go down now, is the marketplace sustainable beyond the AI4EOSC project? Will it be integrated somehow into the EOS EU node? So first of all, we have to distinguish that what we are showing, the dashboard and AI4EOSC model marketplace, it's something different than the EOS portal, and I think that people understand that, just in case. And so first of all, we are currently now visible in the EOS portal marketplace as kind of that you can order the service, you can as a link to the actual set of the services. And as the portal will go down, we will be, I mean, the AI4EOSC platform will be still there, and you will be able to use it. And so we are planning to have it sustainable beyond the AI4EOSC project. It is already several initiatives where, first of all, from historical perspective, this is already a couple of years where this was initially developed, some of the components and are online, and there are even more projects, and we'll see example of one of the projects in a moment that are keep using it, customizing, extending. So we believe, and also the institutions beyond these tools would like to keep it sustainable. So I hope, and we also are looking for EOS node and are looking for the integration as only this will be available. We'll be looking forward for the methods to do so. So I don't see any next question now. So what I would like to thank you, Daniel, again for your presentation and demonstration. And now we move to last
Thank you so much.
So I'd like to welcome Enoc Martinez. That is, and he has the PhD in electronics from the Polytechnic University of Cantabria, and his fields of research are underwater sensor systems, marine data management, and AI applied to underwater imagery. So, Dr. Enoc Martinez, the floor is yours. You can now share your screen. We can see it now. And I would like just to remind before you go on that everybody can ask questions through the Slido, and that there is also the poll towards feedback towards us for the next series of webinar. So thank you very much for all your responses. This will be taken for sure into account and considered. So thank you. So yes, so please.
Okay, thank you very much. So I'm going to talk about how to train AI model, a YOLO module, and I'm going to use it in the marine context because of I'm working at UPC, but we have this seafloor observatory, which is called OPSI, which is an underwater cabled observatory located at the northwest of the Mediterranean Sea. So it's close to the coast at a depth of 20 meters, and we have a lot of different parameters being acquired there from temperature, salinity, chemical compounds in the water, but we also have video cameras, and we are using these cameras to do ecosystem monitoring. So we have been acquiring pictures since 2011, first with low resolution cameras, now with 4K cameras, and we are using these pictures to assess the health of the ecosystem by doing fish abundance and behavior studies. And as you can imagine, if you have to analyze tens of thousands of images, is a very time-consuming task. So traditionally, the ecosystem monitoring was done in this way, with this workflow. So we have some underwater camera taking some pictures, which are stored and then transmitted to the shore. And then the scientist downloaded the pictures and manually started to count every single fish in the pictures. Meaning that I take this picture, I count all these zebra-like fish, I look in the table for the name of the species, and I update the cell in my Excel spreadsheet. As you can imagine, doing this for tens of thousands of images when you have hundreds of different species, it's a nightmare and it's incredibly time-consuming. And scientists spend all their time almost doing this manual counting before they can get to this time series, which is what they are really using for doing science. So they just need the time series so they can run some correlations and to assess the patterns of the ecosystem. So the traditional way to monitor an ecosystem is very time consuming. It's not even reproducible because when I look at the picture, I may overlook some things. I can do real mistakes in confusing one species by another. And people that needs to do this task of identifying fish really need to be an expert in biology, because there are a lot of different very similar species, but that has to be counted differently, and it's a very, very repetitive task. So to avoid this situation, we want to apply AI techniques to automatically process these pictures. So we want to move from the traditional base, so people counting fish basically, into an AI-based system that has this kind of workflow where we have the same underwater camera taking pictures, but instead of having a scientist spending 8 hours a day counting fish in pictures, we want to deploy a machine learning model that automatically detects and classifies all the fish in these pictures. And of course, instead of saving this into an Excel spreadsheet, we can use a database, and then we can automatically produce this abundance time series. So as you can, and this is a fully automated workflow without human intervention. So when we compare the traditional ecosystem monitoring with the AI-based ecosystem monitoring, we find that, of course, there are some drawbacks in the AI-based. Mainly, you need some strong IT skills. You need a lot of effort to set up the system, but once it's working, you have a fully automated workflow. and you need human intervention to count all the fish. So scientists can really focus on doing science and to making data analysis and not just spending countless hours counting fish in pictures. This work is part of the imaging project, which which wants to deliver artificial intelligence service for marine sciences, specifically for image processing. And well, it is using the same EOSC platform, was customized for this project. So this is partially a response to the previous question. This platform is already being used beyond the project. And other initiatives are also reusing the same infrastructure. So we hope that this will be sustainable in the long run. Here you can see on the right the different use cases, and we are the fifth one. So the one here, the ecosystem monitoring. If you want more information about the project, you can scan the QR code. Okay, when we talk about object detection, sometimes, I don't know, for some people in the audience, this may look trivial, but I think it's good to have an overview on the whole workflow, on how this is done. So if you want to deploy an object detection model in production to do some task, first, what you need to do is to have some data, collect some pictures, and then to label the data. This is the more time-consuming task from the user point of view. So we have to select all the regions of interest and saying, okay, this is an octopus, this is a sardine, or whatever. So we need to transfer our human knowledge to some sort of structured format. Then we need to select a model. There are hundreds and even thousands of models out there, so it's not trivial to pick one, but well, it's essential that at some point we decided which model to use. In our case, we are using YOLO V8. And then, of course, when you have the model, it's probable that you have to do some transformations with the data, meaning adjusting the formats, the files, etc. And here it comes the most computing intensive aspect, which is the training of the model. So you're basically taking your label data and putting it into your model. And after some hours of computation, if everything goes as expected, you will have your trained model that you can use for inference. And you can have, in our case, for instance, we can see here a picture with some fish, and the machine is able to automatically detect all of them. How to select a model? Well, that's a tricky part. There's the AI field is huge, and it's rapidly evolving. And there are hundreds or even thousands of open source tools ready to be used. So if anyone is thinking about deploying a new AI-based service, I encourage them to browse this page, which is Papers with Code, where there's a huge collection of different models with the code and the data, and you can see several benchmarks that may help you to decide which model is better for your application. In our case, we selected YOLO V8 because it has a good balance between the precision of the predictions and the speed. The speed meaning the computing requirements. So it's not very CPU consuming for inference. It's quite easy to use, and it also has good documentation, which is also very important for people like me that we are not experts on artificial intelligence, which for people that we only want to use the models. So some comments on things that are important when you train a model. So if you take a look at the documentation, train is just one single line. You say, train, here's my data, and everything works. But of course, this can be fine-tuned to have better results. For instance, we have been playing a lot with the different training parameters, and the main ones are, of course, the number of epochs, meaning the number of iterations that your model is going through the data. So if you have 100 epochs, your model will go 100 times over your training data set. Usually between 100 and 200 is okay. We also struggled quite a lot with the image size because some models favor speed and precision, and what they do is they reduce the quality of your images, like you see here in the fish pictures. But if you are not careful, you may end up losing a lot of information. If you have a small fish far away from the camera and you start reducing the quality, you will end up with 3 black pixels, which are impossible to distinguish. So in our case, we struggle quite a lot, and we find out that the best way for us is to use the higher resolution possible. And of course, the batch size is also something that you can take into account when training. Once you have a model trained, then you will need to take a look at all these complex metrics. So precision, recall, IOU. So I'm not going to go into the details, but that's something that also you will need to learn because you need to know how good your model is, and you need to compare it to others. So we are using MAP, which is mean average precision, to compare our model with different training sets and different algorithms. And this is some results that we have. Here you can see a video that we acquired last summer. We have a lot of fish around, and our model can detect them, track them, and as you can see, it works reasonably well. As I said, we have issue with the small fish in the background because there are just a couple of pixels, so it's still really difficult to detect them. But still, with the fish that are close to the optics, we are having a very good results. If you scan the code, you can go to the YouTube video, where you will see the whole video, and we have all the links there with the models that we use and everything. Within the imaging project, we are using, as I said, the same platform, but just customized for the project. Within the platform, we have the dedicated resources for training. We have also some off-the-shelf AI models, and most of them you can interact with them via command line interface and or API. We will see it in a minute in the hands-on section. And of course, all the code is publicly available. Everything is on GitHub. Since everything is based on Docker containers, if you don't have access to the platform and to the resources, you can just go to Docker Hub, pull the Docker image, and you can run it in your own computer. So everything is pretty much reusable. So now let's go to the hands-on section, where I'm going to show you how to actually train a YOLO V8 model. So first thing, we need to go to the platform. Here you see a very similar, it's a very similar as the AI4EOSC platform, which is in fact the same, but this one is customized for the imaging project. We have different modules, and I'm going to select YOLO V8 module. Okay, we have some information, the link to the GitHub, the link to the Docker Hub if we want to run this in our own computers, and we have this nice train module as we saw before. If we click, in this case, I'm going to show the training via the command line interface, and I will try to make it as simple as possible, but still, just Jupyter training test, some password. We can add some more information like description, domain, etc. So if we click next, we have this second part of the wizard is about hardware. We're going to ask for more CPU. Of course, if we want to train on a lot of data, GPU is advisable, but in this case, we're just going to do a small test. We also can configure the RAM memory, which 8 GB is fine in this case, the same for disk. And for storage, this is meant to transfer huge volumes of data between your container and some other repository, which we are not going to use. And just click submit, and in a few moments from now, we should see, okay. And the model is here spinning up. So to make this quick, I already deployed previously a model, the same model, which is this one. I'm going to open. Of course, we can take a look at the details here. We can see the CPUs, memory, etc. And we can click on the IDE, and it will send us to this Jupyter Lab. Okay, this works. This is basically just a Docker container with the YOLO V8 package installed. That's it, nothing else. And we can train our data here. So the next thing, once we have the model, we need some data to train. So I'm going to use this data set, which is it's a very small data set, just with 20 pictures with different fish labeled. For instance, this is a then text, this is a chromis, whatever. So I have to import this to the platform. I have over here, this is my data set. Let me just drag and drop, it should work. Okay, I'm going to just going to export my compressed file. Okay, and here we have our pictures. Okay, yeah, this is it. There are a lot of tools that automatically convert your pictures with the labels from one format to another. So I'm just using RoboFlow to automatically convert all my labels to YOLO V8 model. And now we have here, inside we have the .yaml file required, where it says where are my images, the names of my classes, the license, and the URL to download this. Okay, and the next thing that we need to do is to train this model with YOLO. So I'm going to go to the official YOLO V8 documentation. Okay, this is YOLO V8 documentation. Here, a bunch of information on how to install it. Since we use the YOLO V8 model, it's already installed. And okay, here we see all the different tasks that we can do, and we want to train. It's as simple as that. So I'm going to copy the train. So it's YOLO train. Instead of this Coco dataset, which is a forward, I'm going to put the path to my dataset, which is YOLO V8 AI4EOSC dataset, and it was data.yaml. The model, YOLO has several flavors. We're going to use the nano one, which is the faster. It's the fastest one, just for to display how it works. And epochs, I'm going to put just 3 epochs to make it really, really quick. So this is now it's only training with 20 pictures and 3 epochs, so the results are going to be quite bad, but still you will see how this looks like. We hit enter, it downloads the base model, starts the engine, and in a minute we'll see this. Okay, and it's just doing the epochs. First epoch is done. Usually this is done with hundreds or thousands of images and hundreds of epochs. So we are just using 20 pictures and 3 epochs. This is why it's so fast. This may take hours usually, but okay. And it's done. And here we have our model. If we go here, we can just list, not like this. We list runs, detect, train. Okay, and within weights, okay, here we have our model. This best.pt file is the actual model. So this is quite bad because we are only trained with 20 images. I'm going to upload a previously trained model, which I know which is much better, which is this. Is this OPSI Nano model here. And I'm going to run some detection with some sample data. I don't know, for instance, this picture. I'm going to upload it here. And if we, okay, we have the picture here. Okay. And if we go to the, not here, to the YOLO documentation, instead of training, we already have our dataset trained. What we want to do is prediction. Okay. So let me copy this, copy. Let me go back to my terminal, clear it. And now we need to fine tune these arguments. Of course, I don't want to use the default network. I want to use my train model. That's why we are training it with our data. And we don't want to use any YouTube video. We want to use our picture, which was its name something like P8 set 2023, something like this, yes. And as I said before, the image size, if you want to detect a small fish as well, it's really important to use the higher resolution as possible. So I'm going to put 1900 pixels. And with this, okay, because we are not here. Okay. I'm in the wrong folder. Change this. Okay, good. Not very spectacular at the moment, but we have this sentence saying results, save to runs, detect, predict, and here we have our data. Okay, so it's working. We have our data with predictions. So this is the way to train and to interact with the code with a command line interface. Not very appealing, not very nice, just a black screen with white letters, but still it works. So if we don't want to use the command line interface, we can also use the TPAS API, which provides access to these modules with an API and also with the user interface, and we can include this API into our workflows. So what I'm going to do now is to deploy another module. In fact, the model that I showed you is this one, which is already published in the marketplace. So we have trained a YOLO V8 with our data and published the model with the YOLO V8 trained for our application. And we could deploy this, but I already have one deployed just for the model, and here it is. OPSI fish detector with DPAS. Okay. DPAS is the name of the API which we are going to use, which is basically the same as the previous tutorial. And I'm going to be really quick. First, what we can do is try. So this is just the user interface, but it can be automated, of course. Here we see the commands to how to make this from the command line or to include it in your code. For instance, I'm getting the list of the models included, and since we are using this OPSI fish detection, it's small here, but we have 2 different versions of the algorithm, and this is just to know that we are in the right place. And now I'm going to show you how we can do some predictions. So let's take some data. No, let's take this picture here. Okay, and here we go. Here we can select, all these are different parameters from YOLO. Of course, we could spend a lot of time talking about all the different minor differences that it could make to select one or the other, but I'm just going to show you that it works. And we have different output responses. So let me select image PNG, because if I select, for instance, JSON, it's going to just give me a list with bounding box, but I want to see the image to see that it's working. Okay, I hit execute, and okay, and here we are. We have our picture with a lot of nice bounding box with all the fish properly detected. This is not only as I said, if I select, for instance, JSON, it will return me a text-based output with all the different inferences and all the different classes of them. It could be useful if you want to embed this API into some more complex workflow as we do. And a very last example, I'm going to show you that this is also possible to do it with the video, as I showed in the slides. So I selected a video, and I'm going to select also video as output and run. Of course, it's a video. It will take around 1 minute because it's 30 frames per second. So it's a 10-second video. It's this one. So it's actually running 300 different inferences. And in a minute from now, we should be able to see this, but with all the bounding boxes around the fish.
Okay, while we're waiting, maybe I will ask you a question that are from audience.
Yeah, sure.
Are there any plans to apply AI on the resulting time series data itself, so sort of predictive maintenance?
Okay, it will be really nice. I mean, yes, it's also possible, of course. Okay, just before we move on that, let me just show you the output of the video. Okay. Okay, and this is the result of the inference. So the same video, but with all the fish detected. Okay, let me go back to my slides. I'm just going to read the conclusions, and then I will answer the question. So as a very fast conclusions, this platform provides a user-friendly and easy way to use it, to deploy models, to train them. You can find a lot of different pre-trained models that maybe they fit your purpose, and if not, you have on-demand resources for training and for running inference. And you can do it with the graphic interface, with the API, or even the command line, as you wish. So that's all I have for plan for today.
So thank you very much for it. I think it was a very impressive whole demonstration and presentation. Online demo, really, it's very impressive also with this video. So now we can come back to the question that we had from the audience.
Yes. So of course we could also. So this is just to produce the time series of the data, and of course we could also use another models, AI models, for the analysis of the time series. Unfortunately, we are not there yet, but it's a good point, and we would be really happy to apply these techniques as well for data analysis. But we didn't have the time to do it yet.
Okay,
for
so
predictive.
Okay, please.
And for predictive maintenance, it could be also used, but we are not really focusing on let's say, of the status of our infrastructure, like the physical systems underwater. They require a lot of maintenance. It could also be useful for predictive maintenance, but what this particular application is focused on, ecosystem monitoring. It could be done, but it's not what we are trying to achieve.
Okay, thank you. Another question, what tool are you using to label the images for training?
Okay, I know that there are a great deal of tools out there. We started using RoboFlow, which is actually this tool. This is called RoboFlow, but we found some minor issues that we didn't like. And of course, if you wanted to get rid of the minor issues, you had to pay like I think it was like 200 euros per month to have like the premium versions. It's quite expensive. And we end up using, I think it's Label Image, which is a simple Python tool. Just it's like a simple but effective tool to label our data. And we are even running our algorithm, so we get the results, and we have some kind of semi-automatic labeling system that helps us label more data. And we integrated it with the Label Studio. I know that there are also CBAT and Label Image, but there's a lot of there.
Okay, thank you. Thank you for this response. So we have another question. The results of the video you have shown are very interesting. What is the volume of the data needed to obtain this kind of results?
So, okay, for instance, it really depends on, for instance, this video that I showed here embedded in my slides, it's a data set with only 400 pictures. Now, with our latest model, we are around 3,000 images. So, to have some, let's say, good results with few hundred images is enough. But of course, if you want to improve and you want to refine your model, you will need more and more data. But with a few hundreds, it's possible to achieve pretty good results.
Okay, thank you. And I think there is some final question. In addition to YOLO, what are other state-of-art models should we analyze in relation to real-time object detection systems?
That's a very good question that I don't have the answer for. My field is engineering applied to marine sciences, so I'm not really an AI expert. But what I suggest you is to go to these papers with code benchmark website where you can select object detection, and you will see a whole lot of different models there with different benchmarks, with different data sets and different metrics. So I think if you want to start doing some application and you are not sure which model to try, I would suggest to go there and to check the benchmarks with different models.
Okay, so thank you. That's it. Thank you so much for this demonstration, all the responses and presentation. So before we finish today's session, I would like to invite you also for the next webinar that will be on the 22nd of April on federated learning. And I would like just to remind, and maybe I will show also reminder slide about the basically, just a second. I don't know if you can see on my screen. Okay, just a reminder about, okay, the webinar that is this 22nd of federated learning in the EOSC, and then about open call for new use cases. So if you are interested, please apply. And I think that's it from my side. I don't know if Alvaro or Judith or Valentin that are also present here would like to say anything in addition. Okay, if not, then I would like to thank you very much for your attention, for participation in this webinar, and for all your questions. So please join us in next webinar. Thank you and goodbye.
Bye.